In this video, I'm going to be doing the first example of what I call the Newton's laws triple whammies, where you have to talk about all three of Newton's laws in a qualitative problem. So, number one, a rocket accelerates by burning fuel and expelling the exhaust gases out its back end with a large constant force. If a rocket begins at rest in outer space, where there is no gravity, and I'll also say there's no air resistance in outer space either, and begins with 90% of its mass being fuel, describe the motion of the rocket over time during the fuel burn, and also after it stops burning fuel. Use all three of Newton's laws in your explanation. So for these kinds of problems, I'll normally set a table up for you so that you can help organize your answer and so that you also kind of know what you're expected to talk about. So this question asks us to describe the motion of the rocket. Okay, describe the motion of the rocket. And we want to do it during the fuel burn and also after it stops burning fuel. So it really wants us to talk about four things that's kind of summarized in this table here. Okay, so how is the rocket moving during the burning of fuel and then after the burning of fuel? But then also relate it to Newton's laws. Okay, so why is it moving that way? Explain using Newton's laws. So before I start typing in here, I'm actually going to show this picture I made. So first of all, I should say that the rocket icon I got from a website called the Noun Project. That website has a lot of nice icons, like these little black and white pictures that you can download for free, and as long as you credit the creator. So this was created by the user whose name is Vectors Point. Okay. So I talked a bit about the rockets in my last video with the Coke bottle, but what happens with the rocket is that it's got fuel in it, and as the question said, actually about 90% of the mass of the whole rocket at the beginning consists of fuel. And then when it burns the fuel, it creates all these hot gases and a lot of pressure, and the gases get shot out the back here. Okay, the gases get shot out the back here. So in essence, the rocket applies a backwards force on the gases, and due to Newton's third law, the gases would apply an upwards reaction force on the rocket, and we actually call that force thrust. That's just the language we use for the force on a rocket. I made up some example numbers here. I know when we type the answer, it's only going to be qualitative, but I just made this to give you an idea of what's going on here. So at the beginning, time of 0 seconds, let's say that the mass of the rocket is 3 million kilograms. 10 to the exponent 6 is a million. So we got a mass of 3 million kilograms, and most of that is fuel, actually. And it burns the fuel and creates a force of thrust. And let's just say that the net force created by that thrust is 30 million newtons. So then we can calculate the acceleration with Newton's second law. 30 million divided by 3 million gives you an acceleration of 10 meters per second squared. So that might be the acceleration near the beginning there. And then this over here, the rocket has gone up a bit. And I just said, let's say 60 seconds has passed, or some amount of time has passed. So the important thing to know is that as fuel is burned, the rocket loses mass. And since it has less mass, the acceleration is going to get bigger because of Newton's second law. Okay, acceleration equals force divided by mass. So mass is in the denominator. So if the denominator is smaller, then the acceleration is bigger. And these are just some example numbers. So let's say after it's burned fuel for a minute, that the mass is now down to 2 million kilograms. and the force of thrust is remaining the same at 30 million newtons. So now 30 million divided by 2 million gives you 15 meters per second squared. So that's what I'm going to be typing in my qualitative answer. I'm going to be talking about how the acceleration actually increases. So at the beginning, when it accelerates at 10, the rocket starts speeding up. And as it keeps burning fuel, it keeps accelerating, but the acceleration's higher. So it speeds up at an even faster rate. So now it's getting really, really fast as time goes on and as the rocket's getting lighter. And in question number 1, we simplified things. Normally, these rockets are launched from Earth, but Earth has gravity and there's also air resistance. So I wanted to get rid of all that stuff to make this a simpler problem. So we're going to assume it's in outer space where there's not those two things. Okay, so let's describe the motion of the rocket while it's burning fuel. So while it's burning fuel, the rocket will accelerate forwards. Okay, rocket accelerates forwards. I'm going to call that point A. Now, why does the rocket accelerate forwards? Well, that's because it shoots the gases out backwards, and then that means the gases apply a reaction force forwards on the rocket. And that's Newton's third law, so in brackets I'm going to write N3. Okay, and now that we have a forward force on the rocket, it's going to unbalance the forces and cause it to accelerate forward. That's Newton's first law. All right. Another detail I talked about in the diagram, so I'm going to call this point B here, was that as it burns fuel, the mass decreases. And as the mass decreases, the acceleration is going to increase. So I'm going to describe the motion. I'll say the acceleration increases as more fuel is burned. Okay, so that's describing the motion. In the diagram, the example numbers I gave was 10 meters per second squared, and then a minute later it was up to 15 meters per second squared. So the relation to Newton's second law, I'll say N2, Newton's second law, says that as the mass of the rocket decreases, because fuel is burned, the acceleration will increase. All right, so that's what happens during the fuel burn. Now, what happens when it runs out of fuel or when it stops burning fuel? The engines shut off. Now, remember, we're in outer space here. There's no gravity, no air resistance. So with no forces anymore acting on the rocket, we go back to Newton's first law and say that it's going to continue in uniform motion. And another way to say uniform motion is constant velocity. All right, and that's Newton's first law. So N1 states that if the forces are balanced, which is true when it's not burning fuel anymore, then the object will remain in uniform motion. All right, so there is example number 1. Okay, I describe the motion of the rocket during the fuel burn and explain why based on Newton's laws, being sure I state specifically which law applies to which part of the motion, and do the same thing for after it stops burning fuel. So in the next video, I'm going to do example 2. By the way, this handout with these answers on it is posted in Google Classroom. So you can access that file. You can make your own comments on it if you wish to add more notes and whatnot. But this is here for you on Google Classroom.